Just here's the plan. This is a great way to do things when you're learning. Uh, in Finland, for example, and I am an advocate for this kind of learning. Finland has the best educational system in the world by far, by far. I mean, their test scores are phenomenal. Kids learn. I mean, they go to the best schools. It's going out of high school. Alec, put that away, please. I don't want to see. Uh, Part of it, if schools pay for everybody, as much schools want to take. But the other thing that they do that's really different is they advocate and they teach students to learn this way from the very beginning, is to be like you would be in athletics. Like when you go into a practice, if you're going into a varsity practice, are you going to go into it kind of half speed? No, you're not. Practice, and good practice don't have to be that long, right? A good practice might be 2 hours or less, hour and a half. But you go into the practice and you work really hard and then you stop and go do something else. While you're there though, you get a lot out of it because your intensity level is high. Same thing with school. It really doesn't make sense. In Finland, they don't assign any homework. No. It's a national policy that there is no homework. What's that? You can go there? Yeah. They build in things like, for example, they build in sort of like recess for people in high school, where there's time unstructured, where you can just go socialize and you can go play video game, I mean, whatever you want to do, but there's a lot of that time built in. And the idea is that that's important to have. When you learn, you're much more effective if you can get away from the learning. This is a trick. When you take a hard class in college, this works. I'm not kidding. When you're studying hard for a big test or something, you put some keys in your hand. This is going to sound stupid, but this really works. Put some keys in your hand, or something that'll make noise when it drops, and allow yourself to kind of just fall asleep. Take a break and fall asleep. When you fall asleep, your hand relaxes and it falls on the ground and wakes you up. That works. The process of letting your mind kind of get away from what you were thinking about frequently allows you to do, there's some biological stuff going on in your head that I won't bore you with right now, but it actually changes the way that your brain wires itself. But from a different perspective, it allows you to kind of unleash the thoughts that you were attached to that might have been incorrect and see things from a different perspective. Has this ever happened to you where you're thinking about something really hard and you can't remember this guy's name or something, right? And then as soon as you get distracted, you go do something else, oh yeah, that's what right? I mean, it happens all the time, right? As soon as you distract yourself and you think about something different, a lot of times your subconsciously your brain will solve the problem. And so, if you take this approach, like in school, I think you're far better off spending 15 or 20 minutes of intense learning and putting it away than spending 2 or 3 hours of kind of crappy, not really attentive learning and not getting much out of it. A, it works better, and B, I mean, I've got a life too, and my family, I've got my kids out, I think there's other things in life that are much more important than math. But math is important. It's an important part of your progression as a student, move on to the next level and go to college, et cetera, but you don't want to contaminate all those other things with the time that you're kind of having to spend on math. If you sit there in front of the TV and you're just kind of casually working through stuff and you're not really getting it, well then why? Instead, go sit down someplace quiet, take 20 minutes, work hard, put it away, and then you don't have to be distracted from other more important things by doing your math. Does that make sense? When I was in college, and I was in an aggressive college, a very academic college, and I was in a study physics, it was I had to work hard. I mean, there were a lot of kids there that were smarter than I was, so I had to work hard. So, to me though, I always gave myself, I worked really hard during the weeks, but I told myself that between Friday at 5 p.m. and Sunday at noon, I was not going to do any school. And I didn't. That was my time to just completely, get away, go skiing, whatever I was going to do. So that was, but the rest of the time I was really intense about getting my stuff done when I needed to. I think you can take that same kind of a philosophy even in high school. And high school is not, college is better. College, you got 3 classes, you probably meet 2 or 3 hours a day. The rest of your time is yours. You got way more time to organize your studying. It's a way different deal. College is a much better learning environment for you. You're this kind of a group than what we're in right now. It's unfortunate, but we have what we have. But when always re-get it. It's like riding a bike. Once you've done it once, it's easy to relearn. It's like skiing or snowboarding or something too. Once you know how to do it, even if you take a few years off, you might be rusty the first run, but you can do it, right? It's something you've learned how to do previously. You can re-get it. So you got it. Your goal is to get it in here, and then you can always re-get it, right? Does that make sense? Okay, think about that. All right, so let's get it. Let's get this stuff. I'll make it as short and sweet as I can, and then let you go practice so you can, kind of practice, get it cemented away in your brain. So what we're talking about today, the third kind of transformation that we haven't dealt with yet, right? We dealt with reflections and rotations. Well, the third one is translation, right? So without reading this, what is a translation? If you were describing this to a little kid, what would you tell them a translation is? What's a translation? What's a translation? Yeah, okay, so it's going from here to here, right? So it's like a slide or a glide. It's like if you took a puzzle piece and you slid it across the table, but you didn't rotate it or anything, right? You just took it and slid it. That's a translation, okay? So, for example, here, if we take this segment PQ, we could take the whole thing. I'm not going to twist it or anything weird like that. We're just going to take it and slide it along. That's a translation to P prime, Q prime, okay? These would be the properties, right? We know that how many points are there on the segment PQ? Infinite, right? There's two of them that are important to us, the endpoints. That's how we label the segment. But in between P and Q, there are an infinite number of points contained in that segment, which is kind of a weird concept, but we've talked about that. Each one of those infinite points, including P and Q, is going to get slid exactly the same, aren't they? When I slide the whole thing. Everybody agree? Right? So if we just focus on the two important points, P and Q, then what do we know? Well, we know a couple things. We know that the distance from the pre-image P to the image P prime is the same as the distance from Q to Q prime. Has to be, right? Everything gets moved the same. We also know that they're slid in exactly the same directions. And so those two line segments, P prime, and segment Q prime, have to be parallel. Right? So there's a lot of the properties that we've previously talked about that we could apply to this picture, right? A lot of it we can just sort of intuit. It's not stuff that's really that majorly difficult to think about. Okay, so we know it's an isometry. All of the measurements stay the same. Okay, so here's the part that I want to kind of show you about. Remember when we talked about the other day, we looked at, where is that? Oh, man.
Oh, and Mr. Oya?
Yeah.
You're supposed to be getting an email from the librarian lady for me. I know that's really random, but I forgot.
Okay, that's fine. I'll look for it.
Okay.
Darn it. What did I do with this? Gosh darn it. I always do this. Okay, so remember this, right? We had why is this not showing me? Mess this up. Okay, so remember the thing we talked about the other day. We talked about how if we took the rotation stuff, if we took a line and we took an object and we reflected it over two lines. So here's going to be my two lines. So we're going to take the blue triangle and let's say we reflect it over the orange line first. So there's the mirror, and then here's what I'm going to reflect. Sorry, it's taking so long. So there it is, right? So there's the reflection. If I take that reflection and I reflect it over the green line, talk to me about that. That's equivalent to doing what else? In other words, say it again. One rotation. Yeah. Okay. Okay, so to get from the blue triangle to the green triangle, I could do those two reflections, right? Or I could do so let's put that point right there. How about? Or I could do what? One rotation. So if the angle between the two lines of reflection is 25.3427, you don't have to do the math, but I could take the blue triangle and rotate it around what point? Where would I put the tack? Okay, good. Where the two lines of reflection intersect. So that's my tack, right? So let's mark the center. We'll put it right there. That's the tack. And I'm going to rotate how much? How much am I going to rotate? Okay, good. I'm going to rotate whatever the angle between the lines of reflection is times 2, right? And that should line it up with the green triangle, right? So let's try that. Rotate. So what's my angle going to be? What is that? 50.6854. And what do you know? It lines up perfectly with the green one, right? Everybody agree? Okay. All right. Okay, so what happens to this if I want you to notice something. If I pull the point of intersection up so it's really close to the blue triangle, it has an effect on the green one. Let's just get rid of the red one completely. It's just confusing. Okay, describe that. So as the tack goes closer, as the tack goes closer to the blue triangle, the green one gets more obviously rotated, doesn't it? Everybody see that? As I move it further away, the rotation isn't so obvious. And if I make that angle smaller, what's that start to look like now? It starts to look less like a rotation from blue to green and more like a what? Like a translation. Yeah, let me ask you a question. So let's say we're going to take a situation where we're going to take a little field trip here. We're going to go up to, we have to probably wait and do this. Well, I guess we could go to the South Pole. So we're going to go down around the South Pole. We're going to go out on the sea ice. Okay, this is our field trip we're going to do. Where the ocean has just frozen solid, right? And if I start, here's the point of this whole field trip. You may not think it's worth it, but I've got my spike shoes on so I can walk on the ice, and I'm going to walk 10 feet in this direction. Describe that transformation. What is it? What's that? There's no polar bears at the South Pole.
That was a translation.
That was a translation, clearly, right? Translation. I started there and I ended up here. I walked in a straight line, right? Okay, sounds good. We're going to do this. I'm going to do this a little differently now though. It's gonna tire me out a bit, but I'm gonna go down there where the sea ice is frozen over a whole huge portion of the earth. So I'm gonna start at one place, and now I'm gonna walk for 10,000 miles. Oh, okay. Is that a translation? Yeah. It is? Okay. Yeah, it seems like it, doesn't it? Be another translation. Okay, but I think maybe you're forgetting one important fact. One important, yeah, I'm just gonna go straight line. Straight line, right? So that would look something like, first one would look like this, right? Here I am. I'm gonna start right here. And I'm gonna move this way 10 feet, right? There's the frozen ocean. I'm standing on the frozen ocean, right? So I moved that far, 10 feet. Looks like a translation, doesn't it? Right? Okay, now I'm gonna walk 10,000 miles. If I walk 10,000 miles, doesn't that look more like that though? Right? I'm gonna start there and I'm gonna walk along the earth for 10,000 miles. Does that look like a translation to you? No. What's it look like?
Rotation.
It's a rotation. Yeah. Good. It's a rotation. And you could kind of get a sense of that if you were watching me do this with a telescope or good binoculars. You wouldn't hardly need those, honestly. You would see that as I walked away, I would start to disappear over the horizon. How come? Yeah, because the Earth's a sphere, right? And so you get a sense without even having for me to have to walk that far. I'd only probably have to walk like 12 or 15 miles. And you'd start to realize, okay, this is not really a translation, it's a rotation. Well, is that really any different from that? I mean, what is the difference? Technically, I want you to change your answer maybe, or revisit your answer. Is that really a translation? No, it just seems an awful lot like one though, right? We could call it a translation and be forgiven because it really does act a lot like a translation. But in reality, it's a rotation, but it's just that the Earth is so big and I'm traveling such a small distance that the curvature is very, very minimal, right? Everybody see that? So isn't that the same thing that's really going on with this, right? What would happen if I took this point right here, that's the intersection of the two lines of reflection, and I move it down there, I drag it down, I dig a hole in the earth and make my board a lot bigger so I go down a couple miles. What's that going to make these lines start to look like? Start to look parallel, aren't they? Right? But what if I did that I took that to the next level. What if I took this point and I drag it that way infinitely far? Infinitely far. If I drag it infinitely far, then those lines actually become parallel, right? And if the lines become parallel, what's going to happen to all that curvature that we see right now? It disappears, right? It disappears because if the center of the rotation is infinitely far away, the rotation actually becomes a translation, right? And so what we could do with this, if I make those lines parallel, well then, if the lines are actually parallel, my double reflection becomes a translation. I want you to make an estimate for me here. What do you think is going to happen if the distance between the two lines, like between points K and I, is 2.72? I guess I kind of gave it away here. What do you think the distance of the total translation is going to be? So once again, what I've done is I've reflected the red triangle over the red line, and then I reflected the blue image over the green line. So I got a double reflection, right? The distance between the red and green lines is 7.27. My question is, how far did I effectively translate the red triangle to get it to the green triangle? What do you think? What's the relationship going to be? It is. Yeah. What do you notice about those two numbers? It's half. Yeah, good. The distance between the lines of reflection is half of the translation, right? Does that make sense? Okay. Now, what's cool about this is it doesn't matter where I put the lines. I could put the lines, like I could move this. What if I move this red line over here? What does that do? Well, it still works. What if I move the red line, move the green line clear over here, like so, and I put the red line way over here? Okay, it flipped them around, didn't it? right? That's weird. Look what it did. So the red one is the in-between one, right? That's the first reflection, and the green one is the second reflection, which is also the translation, right? So in this case, we went from blue clear over to red and then back to green. Everybody see that? Why was it that way? Well, the red line was so far away that the blue one got reflected pretty far, right? The blue one got reflected, so it was actually to the right of the second line. And so when it gets reflected over the green line, it actually moves to the left, back to there. But notice what the relationship is between those distances. Still 2 to 1, right? It doesn't matter where I put them. It's always going to be 2 to 1. Okay? Does that make sense? And I could put this red line a mile that way and put the green one a mile plus that distance, and the reflections are going to be huge, but the green one's still going to end up right there. Okay? All that matters is that those lines are, if they're 2.7 apart, then the translation is going to be 4.8, or whatever double 2.7094 is, right? Okay, does that make sense? All right. So last issue then, and we'll get you out of here. Okay, so that's summarized right here, right? Here's this is out of the book. So if we take the green Pac-Man, we reflect it over the line M, it reverses the orientation, it makes it backwards. We reflect it over the parallel line N, flips it back, right, to normal, and the distance that we move the thing is equal to twice the distance between the lines. Okay?
How come if two translations equals one rotation, but when you rotate something, it doesn't go back to its original?
It does. Rotations don't flip the orientation, right? Right?
Yeah.
Okay. The only one that does is a reflection. Okay. Okay, last issue then. So is how do we represent this, right? We came up with these rules. Remember we spent a bunch of time earlier this week coming up with rules where we'd say something like this kind of stuff, right? Where we'd say x, y transforms to negative yx or something, right? Stuff like that. Got to come up with a rule. Once we get the rule, it's really easy to translate a point, for example. If the original point has coordinates 2, 3, well then what's x equal to? What's x equal to in this ordered pair? 2. Yeah. And y equals 3. So if I want to do this transformation to it, what do I end up with? I end up with, well, let's see, y is 3. I get negative y, positive x, right? Get the idea? Okay, no big deal. How do we do that for translations? Actually, it's way easier. Here's how we do it. This is a translation rule. We start off with points x, y. Then this tells us that we're going to translate the x coordinate 4 to the right. I'm going to add 4 in the x direction, and I'm going to subtract 2 in the y direction. So that's 4 units to the right, 2 units down. That's it.
If x is like 4, and then so you just put 4 plus 4 and make it 8.
It's 8. And if the y was originally 7, then 7 minus 2 would be 5. That's it. And if you look at it, it would just look like this. I've got a horizontal translation 4, got a vertical translation negative 2, and that's where you end up. It's really simple. It's the simplest one to deal with of all the translations, or the transformations. Okay. All right, so that's how, this is what we call coordinate notation, where the values that we're adding to x and adding to y just tell us how far we're moving horizontally and vertically. No big deal. Okay, the other way we can look at this, I'm going to skip through these examples, you don't really need this. The other way we can write these things is using vectors. Now this is, I'm not going to spend a ton of time talking about this, but I want you to be aware that vectors in math and in my physics class, we talk about them every day. Vectors are really important. When we talk about quantities in the universe, talk about quantities in science or in math, there's two kinds of quantities that are important. There's quantities called scalars, which are quantities that only rely on a number. Like if I were to say, for example, what's the temperature in the room? You could say 72 degrees, and that's it. All you need is the number 72, and we all get an accurate picture of what that means. Vectors are different. Vectors we assign to quantities that need more information. They need a number, but they also need a direction. Like, so, for example, if I want to talk about the position of this pen, okay, if I want to talk about the position of that pen, I can't just say a number. A number is not good enough. I have to, instead, I have to be able to define a direction also. So let's say that this is going to be, let's say that that's going to be the origin. That's where we're going to pick 0 to be. We're going to measure everything relative to that point. Well, where is this pen? Well, I could give you 3 numbers that would tell me not only how far away it is, but what the direction is. We have to go a certain amount in the x direction, a certain amount in the y direction, and a certain amount out of the board in the z direction. Or what I could say is, it's a distance of 3 feet away in that direction, right? It needs both a number and a direction. If I want to talk about my displacement, if I start here and end here, it's not enough to just say 4 feet. Because 4 feet could mean, if I start here, it could mean any place in a sphere that's 4 feet away from me is where that could mean, right? That's not specific enough. I have to say that displacement was 4 feet in that direction, right? So vectors require both a magnitude, which is a number, and a direction, right? That's perfect for a displacement, isn't it? Right? Because if you think about a displacement starts at a place that we call the initial point, and it ends up at a place where we call the final point, or the terminal point. And it went a certain distance, but it also had a specific direction, right? And so it's really easy for us to represent this translation as a vector. We could call this vector PQ, okay? Which we would write like that. PQ with a little arrow over the top. It looks like a ray, okay? Here's the notation we use. What do you think that means? So I'm going to write a vector using this bracket notation where I've got a pointy bracket to the left and a pointy bracket to the right. That means component form or vector form. What do you think the 5 means? What do you think? Nick, what do you think that 5 means? Okay, well, because of the symbols. Okay, ignore the symbols for a second. That looks like an ordered pair though, doesn't it? Right? 5 on the x-axis. Yeah, so this is the same thing as saying xy translates to x plus 5. Those 5s are the same thing. And if this were like a -3, what would that mean? Y minus 3. Only now this is a little more compact way of doing it. We don't have to write the x's and y's. It's just telling us that in the x position, that's telling us how much we're sliding in the x direction, and that's how much we're sliding in the y direction, right? That's it. And these don't mean less than and greater than. They're just like funky brackets that tell us that, okay, this isn't a normal ordered pair. This is a vector. These are the components of a vector, right? So that's how we would write this translation. Does that make sense? When you put these in Moodle, how do you think you're going to make those brackets? Yeah, with the less than and greater than. They're just right on the keyboard, right? Okay, make sense? Okay, I'm going to cut her. I think that's good. Let's get in there and work.